Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll continue talking about cluster analysis in Chapter 14. In this video, we'll come down to identifying the number of clusters, but I'm going to start by motivating this example with some data, and I'll scroll up to an example of mammal teeth. So in this data set, we have mammal teeth, and we have 8 types for 32 different mammals. We have the top and bottom incisors, which are V1 and V2, the top and bottom canines, V3 and V4, the top and bottom premolars, which is V5 and V6, and the top and bottom molars, V7, V8. So if I scroll on down, we see that definition here as well. So incisors are basically your front teeth, canines are your pointy eye teeth in the corners of your mouth, premolars are behind your canines, and molars are behind that. And here is the table with the data. So we have bats, rabbit, squirrels, raccoons, otters, cougars, seals, reindeer and elk, deer and moose. And I'm going to start by looking at a tree, the dendrogram, with average linkage. So some things that we can see in the clustering here is like the reindeer, elk, deer, and moose. All those bigger animals seem to group together. All the bats are over here together. Let's see. We have the seals and sea lions over here. The jaguar and cougar go together. It's sort of nice. Lots of pairings that make sense to me, at least, right away. Calculating that was, so let's see, I remove the first column of the teeth data set. That's because the first column of the data set had the names of the animals in there. We just want the numeric columns. Calculate that distance matrix, go ahead and do the hierarchical clustering, and the plot there creates the dendrogram, and the labels for the tips of the leaves of the tree are the first column of the teeth data set. And that's what we saw here. One thing to note is we have a height here, which is the distance between pairs of observations, and you can see lots of connections right there at the bottom. That's because the number of teeth that the cougar and jaguar have are identical. So they are 0 distance away, so they become a cluster immediately. In the scatter plot, they would be 2 points plotted right on top of each other in this 8-dimensional space. And I want to look at the data just a little bit more. We can see here for the different types of teeth, this is the number of teeth that each animal has at those locations. For example, some of these animals don't have any canine teeth. It's sort of interesting to me that some have an odd number of incisors, those front. Oh, that's these teeth here. Brown bat has 2 on the top and 3 on the bottom. Sort of interesting. All right. So when we look at this dendrogram, how many groups of animals are there? Well, if you look at the very bottom, there's about 30. If you look at the very top, there's 1. What is the optimal height here to slice across to cut our tree into those clusters? That's the question this section will answer. Though I'm not going to give you a great answer, because there are, just in this one package, NB clust, there are 30 metrics for trying to determine how many clusters there are. So there are so many algorithms that for identifying clusters that it's hard to make a simple, clear distinction here. But we can get a lot of suggestions from this library. So we'll go ahead and load this package nbclust. And when we look at the structure of the teeth data set, we see that these are numeric, or rather integer valued columns. And nbclust does not like integer. When I first ran this function and I kept getting the singular matrix that it couldn't calculate the inverse for, man, I really banged my head against this for a long time, because to me an integer is a type of number, so we should be able to calculate with it. But it turns out that you actually need in this package to make this numeric. So if we make this matrix numeric and then run nbclust on it, it works just fine. We get some warnings, but those warnings are totally what we'd expect. We're going to use the average distance metric, and I'm going to output all of the indices that this package has. So there's a few warnings here at the top. We also get some summaries. Among all the indices, it gives us some results. One of the methods proposed 4 as the best number of clusters, and 5 methods proposed 5 as the number of clusters. And so the conclusion is that if we use the majority rule, that 5 is the right number of clusters for this data set. Now, we're human. In many cases, we're smarter than the computer. And so you want to use 5 perhaps as a starting point, and then consider, what does 4 look like? What does 6 look like? And use your intuition about your domain knowledge of the data set to make that choice. Here is the output for the best number of components for each method, and there's a table here with 2 rows. It has the number of clusters, and then it has the value of the index that is being calculated, and then these columns, the Kullback-Leibler distance, CH, Hartigan, the cubic clustering criterion, and so on. These are all different indices, or different methods of calculating the number of clusters. And you can see right here, the KL distance was 5 clusters, CH was 5, Hartigan was 4 clusters, cubic clustering criterion 5 clusters. So there's lots of 5s, 1, 4, and then sometimes these methods don't converge to give you an actual answer. Negative infinity basically means that we didn't find an estimate. Some of these methods are suggesting a very large negative number of clusters. Okay, negative 9 times 10 to the 14. Same thing with Friedman. So, these are not values to be trusted, I think. Also, zeros indicate not very informative number of clusters. Same thing with 1. This is a half a cluster. Okay, so some of these don't really help. So some of these at the top here are ones that tend to work a little bit better. I really like the cubic clustering criterion, and maybe that'll be basically my final suggestion here, other than to go with majority rules as a starting place and then be a human and pretend you're smarter than a computer. Along with the output, there are some plots. For example, the Hubert statistic depends on the second differences of a particular index, and it's this peak that it suggests. So here 4 clusters is the right number. For this other method, the D index, the second difference, this peak is at 5 clusters. So you're going to get some variability between methods of estimating numbers of clusters, and you just have to be smarter than that. So here are some suggestions about how to interpret this stuff, and I basically gave my suggestion already. Let's plot the suggestion of five clusters. So we'll start off by calculating the distance of the teeth data set, removing that first column with the labels, and use the average metric for the distance between clusters and perform the hierarchical clustering, create the plot with the 5 clusters, and rectangular hierarchical cluster, this will append or add on top of the dendrogram red squares or rectangles. And this top line is effectively the cut point for where the clusters are cut. So you can see it goes through 5 black branches using the top of those boxes. This is our result. We have all the deer, reindeer, elk, and moose in one. We have beavers and groundhogs and squirrels in one. We have all the bats in one, which is beautiful. Moles, pika, and rabbits. Is this anything related to Pikachu? That's sort of like a rabbit-y character. And then sometimes you get like a miscellaneous category. But let's see if this makes sense. We've got seals, otters, weasels, and badgers. Those are, in my mind, sort of similar. This otter, the river otter, didn't make it over with the sea otter. Wolverines, I guess it's probably closer to wolverines. That makes sense to me. The seals are together along with the sea lions, and the raccoons, wolf, and bear. Okay, so there's some sense in this. How all of these groups sort of get together is not that clear to me because I'm not an animal biologist who knows enough to make a lot of sense of this. Some of you in biology listening to this will say, oh yeah, all these things make sense because of because you know the evolutionary histories, and this dendrogram of teeth might follow more generally the phylogenetic trees. The next plot is in this code here, the clus plot. We've seen this before earlier. This is what these look like in terms of their first 2 principal components, component 1 on the horizontal and component 2 on the vertical. And one detail to note here is this number 2, which is in this cluster with observations 7 and 8. This 2 looks really close to cluster 1, but we're only looking at 2 of the 8 dimensions of teeth. So you can imagine this number 2 perhaps being way in the background, and all these observations, or this group 1, being much closer to us. So they're actually separated in space, but the projection onto these two dimensions doesn't capture that particular distance. But otherwise, we see some really nice separation in terms of the first 2 principal components. I wrote some code here that would actually print out the cluster number and then all the observations in each cluster for their numbers of teeth. So you can see how similar these groups of teeth are. Among the bats in cluster 1, you can see among the 8 types of teeth how similar bats are within themselves. Similarly for cluster 2, these 3 animals, they match on most of these pretty closely. So you can see what cluster analysis is trying to do is, in a sense, minimize the differences within a cluster. Observations within a cluster should be as similar as possible. But then, between clusters, there should be big differences. If we look at this first cluster and the second cluster, the main difference is that V3, V4, those canine teeth, are basically different between these 2 groups. Otherwise, these 2 groups are not that different from each other. And so you can spend a little time and see how these groups are similar within and then different between. That's the end of this video. I'll come back and we'll do a big example about birth and death rates for many countries in the world.